Well, I sent out an email over the weekend, and I hope everybody saw that one, describing that I have decided to make the research paper optional. And so if you were counting on that assignment to bring up your average in the course, you can still feel free to do the assignment, or if maybe you've already done the majority of the research and you just want to plow ahead anyway, I would fully embrace and encourage that. But if you haven't done the project yet and you don't want to, it's optional. So there's that. If you have any questions, you can get in touch with me and we can discuss it. Homework number 10, where you are applying the rational method, the National Streamflow Statistics, and TR55 approach to a watershed of your choice. That assignment's due on Wednesday of this week. And we're going to continue talking about WMS today with the HEC-1 model. And so before I begin, are there any questions that anybody would like to ask about the announcements? I'll listen very carefully for that incoming chat sound, and I don't hear it. So interject if you do. All right, so HEC-1 is a far more sophisticated rainfall runoff model than any of the approaches we've seen so far. Remember, we started with the rational method, and the problem with the rational method is it's going to usually overestimate your peak runoff because it assumes a constant rainfall intensity. And then the other issue with the rational method is that we don't have a repeatable and reliable way to estimate C values. And so moving on to National Streamflow Statistics, it's fine. The issue there is that it treats every watershed about the same in terms of land use and soil type. It only looks in West Virginia's equations at the relative area of the watershed. So it doesn't have a lot of variability across the state in terms of the types of factors it's taking into account. The issue with TR55 is that we can only put in a storm amount, and we don't have a lot of control over the temporal distribution of the rainfall. And so HEC-1 is a lot more powerful than any of the methods that we've mentioned before, and we're only going to get into some of what makes it unique. It has a lot of functions and features that we're not going to be able to address in the 2 days that we have allocated to it. So to show you the specifics about the HEC-1 model, what we're going to do is begin by delineating a watershed at the described location here. I tell you it's at the intersection of Garrison and Crescent. So those are two streets in Charleston, West Virginia. That's just on the north side of Interstate 77. So I'm going to pause from speaking. I'll pause the recording, and without me describing every step in that process, because I know you can do it, everybody successfully delineated the watershed in the exam. I'd like you to delineate the watershed that outlets at Garrison and Crescent, just north of I-77. And so place the outlet just on the north side of the interstate. Let's say, for instance, if we were interested to find out what was going to be the flow as it goes under the highway there. So what you shouldn't do, though, is compute the curve number. We'll do that together, and I'll show you the rest of the HEC-1 tools starting at determining the composite curve number for the watershed. So I'll pause for now and then maybe give you a 5-minute head start, and then I'll begin going through the process of delineating the watershed so that it's included in the recording. Garrison and Crescent, Charleston, West Virginia. Alright, so if you're having a hard time finding the project location, let me just illustrate where it is. You can see here's Garrison and there's Crescent. So we want to, you can see, let's see the name of the Magazine Branch. That's an odd name for a creek, but there we have it, Magazine Branch. So we want to delineate the watershed that is this creek just before it goes under Interstate 77. So if you zoom out, you can kind of get a sense for where that is. Bigley, that's funny. We're doing hydrology Bigley today. I think we've got it all in this view. You know, looking at the northern edge of this watershed, I think it terminates here. Let me double check. And you will need to get enough data so that later on we can determine the curve number, but we won't actually use the NLCD or the soil data yet. We are going to use it though, so make sure that you have Surgo and land cover because we'll calculate the curve number. And of course you also need elevation data in order to delineate the watershed. You know, if you didn't have the land cover and Surgo, you can go back later and get it. It's not like you only just have this single opportunity to download the data. And in fact, to demonstrate that, I won't get them up front. I'll just get the elevation data and I'll come back later and get the land cover and the soil type. Compute topaz. Alright, now I have a rough idea, and it does look like I have that entire watershed in the view that I downloaded. I have an idea of where I'll be placing the outlet, but I want to make sure I get the right thing, so I will turn on the online maps, turn off the elevation image. Let's see, here we go. Online maps. Turn on the street map, and we'll just make sure that we drop the outlet just before the creek goes underneath the interstate. Alright, so back to the wizard, and the outlet point we're going to drop right here. Okay, delineate watershed. So it looks like this one is about 992 acres. Okay. And since I didn't get the land use or soil type data before, you'll notice that I don't see in the GIS data, I don't have the shapefile that is the soil type. I haven't created a soil type coverage. We haven't been through that step yet. And in the grids, I don't have the land use data. But I can go into the wizard and go get the data out of the web service. Now this time I'll turn off the elevation data because I already have it and I don't want to bring in a second one. So I'll turn that off, turn on the land cover, scroll down and turn on stats go. No, Surgo. And download. It's asking me for the raster size for the land cover, but of course it doesn't ask that for the soil type data because the soil type data is a vector. So that means it's kind of infinitely precise. When you zoom in, it doesn't become pixelated because the borders are defined as a edge. Alright, and it did that thing where it goes and downloads the adjacent county if you're kind of on the border. So let's look at what we've got and what we need. My project area, it only downloaded the elevation data for what was actually in the view. So as I turn off the unneeded soil type, it looks like here's Putnam County, I think. and then here is Kanawha County. So it's the Kanawha County soil type shape files that overlay the elevation data I have. And so this is the one I need to keep, and this one I can throw away. So I'll right click on that and delete, and now it's gone. And of course it's a good habit at this point to save the work, so I'll save that file. Alright, so I'll pause for a moment. I'd like to hear from everybody when you're at the point that you have delineated the watershed and you have the land use and you have the soil type available, although we haven't yet calculated the curve number. Alright, so we can skip over delineate watershed, select model. We're going to use HEC-1. So over here in the the workflow summary, skip down to the select model text and then click initialize model data once you've done the drop down box and gone to HEC-1. So initialize model data, and so that kind of just creates the placeholder files in the background that WMS is going to use to prepare the input cards for the simulation that we'll run. So you click next. The way that HEC-1 works is you can choose how many iterations to run inside of a project, and you can use historical data that are associated with actual dates. And so you'll notice here that we're telling it the starting date and time of our simulation, the ending time, and then how big each time increment should be. So as a beginning, let's go with the default starting time where it says the 17th of March 2020. And instead of 10-minute, let's change it to say 15-minute though, and then click set job control data. And hopefully, I think what it will do there is it will just set the starting time, and then no, we need to specify a different ending time. So let's choose the 18th. Now this is a little bit different view than I'm accustomed to using it, but the starting date and the ending date. So we're giving it a 24-hour simulation in 15-minute increments, and then click set job control there. Alright, next. Alright, so this is where we're going to go through the process of defining the curve number, because we don't yet have a curve number calculated. If we kind of move the text out of the way here, let me close this and try and move the I'm not having a lot of luck zooming in. There we go. Okay. Yes, with this view you can see it's saying that the curve number is 0. So it hasn't yet calculated the curve number, but it's interesting now that we have a moment to look more carefully at the, let me turn off the elevation data so we can just gaze at the land cover database. So each one of these little squares, remember, is 20 meters by 20 meters. And so it's kind of interesting to look at this and see that the red shaded areas are those that are associated with urbanized uses, and it happens to coincide with where the stream is located. And of course that makes sense to us because we know that most commonly the development, such as a roadway and house sites, are in the flat areas. And the flat areas, if I turn on the elevation map, the flat areas are going to be where the creeks are formed. And so it's still vegetated where it's steep because it's more costly to do the land development there and grading the soil. So you know, the land cover data kind of matches our expectations that we would expect to see the development in the watershed in the same spots that are adjacent to the creek. Alright, so back to the defined land use and soil data tab, because what we need to do is join the NRCS. So click on the join our NRCS there. Now later we're going to click on fill blank values, but not yet, because I want to show you that in this case there is a soil type that it doesn't have a hydrologic soil group assigned for. So leave this unchecked, the fill blank values that normally we will check. Leave it unchecked for now, because I want to just show you something. When we click OK and then create coverages, it's going through this process now of it's created the coverage. Over here on the left side we now have a soil type coverage, and so it's going to map over the data from that GIS file, from the shape file, and so click Next. Now here we have this soil symbol W. It doesn't have a hydrologic soil group for. Remember, these are the abbreviations that we've seen before that have to do with whether it's a blend of like a silty clay or maybe granular sand or whatever the case may be. These abbreviations can be looked up off of the USDA site, and we have a lot of information about the depths that they're usually found, on what slope soil is typically, their adjacency to creeks, and so on. But for whatever reason, in the database for the soil type W, we don't have a hydrologic soil group assigned. So this is an example of it is within our watershed area, a soil type that it does, a polygon that it doesn't have a soil type mapped to. And so that's, it's doing this because we didn't tell it to fill the blank values. And so what we need to do is make the decision of, well, what do we want it to fill with? We could go to the USDA site and learn more about what is the soil type W, and that would be the thing to do. I mean, if you're a practicing engineer and you've got a little bit of time, then you need to figure out what is this soil type W and what are its characteristics. For purposes of today's demonstration, let's just be conservative. And it seems like in this area, the worst case soil type that we have is soil type C. So let's cancel and go back and tell it to fill in the blank value. So cancel, join NRCS again, and this time we're going to fill the blank values. And by default, it's suggesting should it be a soil group B, and with the uncertainty that we have about what is this soil type, let's not choose B, because that would increase the curve number. Now, it would be a minor effect because it's just going to be one of many different soil types within our watershed. But if we say soil type C, then that's a little bit more conservative approach because it's planning for the worst, so to speak. So click OK and then create coverages. Now, unfortunately, it's going to create a second soil type coverage over here on the left side. So we'll have to go through and delete the one that says soil type because it's now soil type 2 that is going to be the correct one that's mapped the way it ought to be. So click Next, and now this time we see that soil type W doesn't have a blank field for hydrologic soil group, but it's now filled in with C because of that fill blanks that we've done before. So since this is a watershed that does have one soil type that's blank, I wanted to show you what are the implications of that checkbox that we've used before. Alright, so click Next and finish. Alright, so we have the soil, and let's delete the soil coverage, the first one that wasn't mapped correctly. So over here in the Project Explorer, if you just right click on the word soil type and then delete, that was the first one, and we still have the second one that we just created, so we're good there. It's a good thing to save your work occasionally, so let's click the Save button and then open up the wizard again, and let's jump down to the hydrologic computations, because our final step is that we're going to want to compute GIS attributes in order to get the curve number. So click Compute GIS Attributes, and we have to import that text file from before. It's the text file that I think I shared with you previously. The name of it, I've got it in here. iwwcurvenumber.txt. So that is the key to the land cover number, which corresponds to a certain type of coverage, and then the soil mapping for the curve numbers. So that is what we need to import down here And it gives it the warning that we're going to overwrite what was there before, and that was nothing. It was blank before, so that's okay. So you select that land cover table, and so if we just look at the summary of what it's using the soil type 2 coverage for the soil type. It's using the grid, and the grid that it has is based on the National Land Cover Database, which was, when you import that GIS data, it automatically maps it into being a land use grid. So click OK, and it will give us the summary of its calculations in this reader, and it looks like the watershed has a curve number of about 68.3. Okay. So by far, the largest component of this watershed is deciduous forest. It has a lot of area as deciduous forest. We even have a little bit of soil type A. Generally, the soil type A would be in the floodplain. That's where you'll see sandy type soils because of the sediment transport and the ability of the creek to move sediment around. Alright, so if we've got the curve number, then we can compute the time of concentration using basin data. So we will compute the lag time not with the Denver method, but we'll use the SCS method. And so you can see it automatically has the watershed length and the curve number and the slope, and any one of these could be overwritten. Like if you click on any one of them, it gives you the opportunity to adjust, so that if you wanted to take the 68.3 that had calculated and say, well, because of my engineering judgment and I know that there's been additional development in this watershed since 2011, maybe I want to take the curve number from 68 down to 65. You can overwrite and calculate the lag time based on an adjusted value. It doesn't have to be on what was automatically calculated, but I'll leave it with these defaults. Click OK, and so it looks like the time of concentration that's based on the lag time, 1.106 hours. All right, click Next. All right. Let's define the precipitation, and now what it's doing is it's bringing up the HEC-1 model. So click Done here and close this. I'm going to show you where you can get to the HEC-1 model directly. We can do all of these things through the wizard, but then there's also the tools across the top, the toolbars and menus. And so right now we are in the map module. Let's change to the hydrologic modeling module, and when we do that, the menu that's across the top is going to change. The tools that we have in the toolbar across the side will change. So click on the hydrologic modeling module, and you can see HEC-1 is the model in this drop-down box. And in the HEC-1 tab across the top, you can go into Edit Parameters, and it will show you what is the window we use for putting in data for the watershed and the outlets. So if we want to use our main, let me turn off the TIFF file. Let's go into the drainage coverage, bring that active, bring it to the forefront, because whether you have the soil type coverage selected, now we're seeing all of those polygons, and it kind of makes the view a little bit busy. If you change to the drainage, then it puts those to the background, and in fact we could turn them off if we don't want the map to be quite so visually distracting. We can turn off any of these things that are in the background if we just want to see the schematic of the watershed itself. Now all I have enabled is just the drainage coverage, and the grid doesn't really show up, so we can, well, I guess it does if you turn it back on. So the drainage coverage is up right now, and so go back to the hydrologic modeling module, and we're going to select the basin. So double click on that brown square, and it brings up the HEC-1 parameters. So does everybody have these HEC-1 parameters up right here? Just to illustrate again how you get them. Just double click where it says 1B, and yours may be named something different. The naming that's used for the basins isn't always clear to me. I think 1B just means the first basin, but if you go through the process a couple of times, like if you redelineate, like splitting a watershed up into sub-basins, then they're going to receive different names. So double click on this to bring up the HEC-1 parameters. Now you can click on each one of these cards, as they're called. You can see here it's saying HEC-1 cards, and the thing I want to point out is at the bottom it's creating a text file for this simulation. And computer programs didn't always used to be visual and with a graphic user interface like they do now. Back in the olden days of watershed modeling, these simulations were done by creating a text file using something similar to Notepad, and you'd type in abbreviations, and then you'd have the parameters that described the characteristics of the watershed. And so you can look and see what's in there right now. You can see it says BA 1.5499, and what that's referring to is the area of the basin. And so BA is an abbreviation that stands for basin area, and 1.5499 is the watershed area in square miles. You'll notice that on screen for WMS it's telling us the area in acres, but it automatically converted that into square miles, which is what HEC-1 wants the basin area to be defined in. So I've in the past described WMS as a watershed modeling preprocessor. And as a preprocessor, what it does is it goes out and gets the GIS data you need in order to create this HEC-1 file. The HEC-1 program is going to look at this file for all of the cards that it needs. And so basin data, you can see it's got the name of the basin, 1B, and then the area. And so if I made a change to the area, then it would change that text field, the preview window, accordingly. But I won't. I'll leave that the way it was. Output control, we don't generally use this output control. It would just change the formatting of the file that it creates after the simulation is run. But precipitation is something that we do want to define, because right now we haven't yet said how much rain is going to go onto our watershed. Click on basin average, and so what basin average does is it puts the same amount of same amount of precipitation over the entire watershed. And one of the cool things about what it will do is we've always had to go to the precipitation data frequency server ourselves to get the precipitation data, but it will do that for us. And so if you click on Get Precipitation from Web, it brings up a little tool that's asking for what storm duration do you want, what return period, and it knows the latitude and longitude of our watershed. And so when I click Get Data, it's going to be going to the same NOAA Atlas version 14 that's behind the precipitation data frequency server, and then it will tell us what is the precipitation amount. So let's do a simulation that's based on the 25-year storm. So if you click on the drop-down box 25-year and then Get Data, it just very quickly pings the server and it gets the precipitation amount 4.162 inches. Alright, so we'll click OK there. And then the other thing that we need to do is define the temporal distribution of it. So if you click on Define Series, this is where it's going to give us the chance to tell it that this is, for example, a Type 2 storm or Type 1A. Or when you click, you'll notice that there's actually a lot of different options available for how you distribute that 4.162 inches over a 24-hour period. And you could do it manually as well with this XY editor. But in Selected Curve, you'll notice that there's a big list of pre-existing temporal distributions. There's some for California on the list. It looks like American Samoa has its own temporal distribution, and it's interesting because what these curves are showing, like the California type 1 curve, it looks like this must be a coastal area, the type of place where the storms are really slow and gradual and it's not intense and all at once. But different regions of California have different precipitation types where the intensity gets progressively more pronounced. So this California 6 looks a little bit more what we're accustomed to in a type 2 storm, where we have the afternoon thunderstorms in the summer that are really intense. And so we know that West Virginia is in type 2. So let's use a type 2 24-hour temporal distribution. And so what it has done in this XY editor is it's defining, remember I had told it that we're going to run the simulation in 15-minute increments, but it's breaking it up into even smaller sizes than that, because this is the resolution that it knows the amounts. So someone has just basically digitized that 24-hour curve. And so when we click OK, and OK here, look what has been filled in the summary window. So all of these precipitation amounts are telling HEC-1 how much rainfall has occurred during a certain time step. And so instead of sending all of the rainfall into this watershed at once, it's going to be sending just a burst of rainfall and then watching how it flows through the watershed in steps. Loss method is already set to the SCS curve number because we've calculated the curve number, and so that's good. The unit hydrograph method, it's using the SCS unit dimensionless hydrograph, and its lag time that's mentioned here is based on the time of concentration that we calculated when we had the wizard open. And if we wanted to, we could enter in information having to do with snowmelt. You know, if this storm simulation was going to be a spring storm where suddenly it got warm after maybe there was already snow on the ground, then you can enter parameters having to do with that, although we don't. So here in the HEC-1 menu, if you click Run Simulation, it will give you the chance to describe where you want these files to be saved. And so let me just make sure that I'm going to put it into this lecture subfolder, and I'm going to call it HEC-1 output. Okay. So I have my location. I'll mention one word of caution, and that is sometimes in the past there have been issues if you put your HEC-1 folder too many subfolders deep. You know, if it's in a subfolder that's within a subfolder within a subfolder, and particularly for whatever reason if you browse and put it in the My Documents, I think because that's buried within folders that maybe have protected write access. Occasionally there are error messages having to do with that. So if you have been saving your work in a subfolder that's many folders deep and has like user protection, you may get an error message. And if that's the case, just create a temporary folder that is close to the root of the drive. Alright, so I'm going to click Save and OK, and it will run the simulation. You can see it says normal end of HEC-1, and it will automatically, when I click on Close, show the runoff hydrograph. So I click Close, and now I've got a hydrograph, two of them on the screen. One that represents what's happening in the watershed, and then the other that represents that same effect at the outlet. And when you just have a single delineation, like the entire watershed is delineated as one basin, then the hydrograph for the basin and the hydrograph for the outlet will be identical. But when you subdivide basins and you indicate lag times between them, then they won't necessarily be the same. But you can see here it's predicting for, I think we did the 25-year storm, that the peak flow coming out of this watershed would be 555 CFS. That's quite a serious storm. And the time to peak 750 minutes. That means 750 minutes after the beginning of the storm. And the beginning of the storm Doesn't, if you look at the 24-hour temporal distribution, it's kind of in the middle of that 24 hours that the SES distribution assumes the intensity gets really high. So it makes sense that we see the peak in the middle of the day. So if we pull up this other hydrograph, it looks about the same. But let's delineate this into an additional subbasin. So let's delete the existing hydrographs that we go to. If in the menu across the top, if you're in the hydrologic modeling module, click on hydrographs, delete all, and it'll make those that are already there go away. And let's drop another outlet midway through the watershed. And so if you go to the choose outlet locations, we're going to create another outlet. And my suggestion is let's put that other outlet in the middle of the reach between here and here. So we'll just put it right about there. So I'm going to create another outlet. Maybe I better turn on the flow accumulation cells. So I turned on the elevation data just so that I'm sure to drop the outlet in the middle of one of those. Okay, so now I've created a second outlet, and I need to delineate another time. The schematic right now is I've got two basins. I've got 2B, so that's this upstream basin, and there's going to be a downstream basin. And then there's an outlet for the first basin, an outlet for the second basin. So I need to delineate the watershed. So choose outlet locations, delineate watershed. And so it's going to give me this warning message that if I do it, it's going to delete the existing stuff. So that's okay. That's exactly what I want it to do. It's going to delete the existing delineation that I had, and it's going through and calculating the boundaries. And now I have two different watersheds. But it doesn't know the curve number for either of them because these are in different spots. And so I have to go through the process of initializing the model for HEC-1. I can use the same job control, so that's fine. I'll click Set just to confirm that it's there. Join NRCS, fill blank values with soil group C, create coverages, next, next, finish. Okay. So the one that it's just created is called soil type, and so soil type 2 was the old one. So I'm going to use soil type when I do the curve number calculations. So click next, and we have to compute the GIS attributes, and I think soil type is the coverage I want to use, and it's going to use the grid data, which is the national land cover for land use, and it still sees the key that I fed it before. It remembered where that was. So when we click OK, I hope what it will do is just give us the curve number for both of the basins individually. All right, so we've got basin 3B and basin 4B. And the curve numbers are roughly equal, 68.2, 68.5. So one of them has maybe a little bit different characteristics. And it doesn't know the time of concentration for either of those because, remember, now it's smaller watersheds. So I'm going to have to calculate them individually using the basin data. So I'll do the drop-down box for the SCS method and click OK, and it knows it for 3B, which is, here we can see 3B. It's the northernmost of the two watersheds. And then do the same thing for 4B. And we'll change to the SCS method. Okay, click Next. And we will define the precipitation. Now, since we have more than one watershed, the HEC-1 parameters are built just one basin at a time. So over here in the Edit HEC-1 Parameters dialog box, you can use previous hydrograph station and next hydrograph station. And so right now, if we put anything in, it's for basin 4B. So that's this basin, the downstream one. So if I go into the Precipitation tab for it, I could choose basin average, get precipitation from the web. Let's again do a 25-year storm. Get data, and it goes and gets the data. We have to define the series. So we'll use the type 2 24-hour series. Alright, so click OK. And now it's built this list of data for just basin 4B. So I can click next hydrograph station, and if we look, now it's saying it's doing it for a reach. So what we're looking at right now is the river that's downstream of that basin. So click next hydrograph station again, and now we're at the data for 3B. And so 3B was the upstream basin. So if you click on precipitation, then we'll use basin average, get precipitation from the web, use the drop-down box to select the 25-year, get data, OK, and then define the series to the type 2 24-hour, OK, and now click OK again. And now what we've done is we've assigned the precipitation to both of these watersheds. And so you can click Done, Next. We don't need to do the cleanup model. We'll run the simulation. So click Run Simulation. Alright. And as soon as we click Close, it will bring up these hydrographs. And so let's close the wizard, and just to get rid of some of this visual distraction, I'm going to turn off the soil type polygons, and now it's a little bit easier to see. I want to check out these hydrographs. Let's see. Select hydrograph tool. So the upstream basin will have a peak runoff of 358 CFS. The downstream basin would have a peak runoff of 345 CFS. Alright, we're almost out of time, so please save your work here. We're going to come back to this when we meet on Wednesday. And what we're going to do is we're going to simulate the delay in flow time between the upstream watershed and the downstream watershed. In other words, how long does it take it for the water to flow from this outlet point 4C? The water is going to flow down the creek before it gets to 3C. So they call that routing through the reach. And so we're going to estimate what are the hydraulic characteristics of the stream that the water is flowing through, and we're going to actually see how the combined flow, right now it's telling us the combined peak is 696. If you add these two together, if you add together the upstream watershed and the downstream watershed together, individually they're each about 350, but then when you combine them together, 696. Well, that peak will be lower because of the travel time and the delay that occurs from watershed 3B. So save your work here, because we're going to get into stream reach modeling when we meet on Wednesday's class. Alright, so before you go, just a reminder that the homework assignment having to do with the rational method, NSS, and TR55, that assignment's due on Wednesday. And if you have any questions about that or what we've gone over in today's class, just let me know. Alright, that's it for today. Take care. I'll see you on Wednesday.